Okay, hello everyone. Today I'm going to talk to you about BlueZ and Bluetooth, adopting a BlueZ project for implementing Bluetooth in production. First of all, who am I? I'm George. I'm a principal software engineer at Collabora. I have been working on multimedia things for the past 14 years. I worked with GStreamer, Pulse Audio, PipeWire. I'm the maintainer of WirePlumber. I've contributed to automotive grade Linux, audio stuff there, and I'm new to BlueZ. Now, in the past 7-8 months, I had a new adventure that stepped out of my audio zone, let's say. I teamed up with my awesome colleague, Kiagiadakis, and together we deployed BlueZ as the Bluetooth stack of a real-world vehicle infotainment system, which is currently going testing for qualification, and as far as I know, it's the first vehicle that is going to actually use BlueZ in production. This project involved actually switching away from a proprietary stack. Previously, that system had a proprietary Bluetooth stack that the customer that we worked with wanted to remove and replace with BlueZ. And the goal was to just implement the same features, nothing different. Along this process, we also had the chance to improve the code base, improve a lot of open source components, and I personally learned a lot. I learned about Bluetooth beyond the audio part. I learned also about audio use cases on automotive, like how the audio DSPs work and what kind of requirements they have there. Now, in this talk, my intention is to pass on what I learned for other people that might want to do the same thing later on, like a change from a proprietary Bluetooth stack over to BlueZ. What should you expect if you want to do that? First of all, let me say that it works. It works pretty well. There is no difference from the proprietary stack. We support media player, phone calls, text messaging, the contact list access, of course, and pairing controllers, like gaming controllers, for example. The architecture that we use looks like this. So inside the Linux kernel, there are some parts of BlueZ. There are drivers that talk to the Bluetooth adapter and implement some protocols. And then on top of that, we have BluetoothD, the main BlueZ daemon, and then we have ObxD that implements some of the profiles for object exchange. For example, the contact list exchange works through ObxD. And on the other side, we have PipeWire and WirePlumber, which was used to implement the audio profiles, namely the A2DP profile, which is the advanced audio distribution profile, which is used for transporting audio from the media player or the video player, and the HFP profile, which is the hands-free profile, which is used for phone calls. And on top of that, there is like some proprietary middleware and UI components that the customer already had, and they just wanted to switch that to talk to BlueZ instead of the proprietary stack that they were previously using. As part of this process, we added some new things. First of all, we added telephony support in PipeWire in the hands-free profile implementation. Like the hands-free profile implementation was already there in PipeWire, which it was being used for enabling headsets. So if you have a Bluetooth headset and you want to enable bidirectional audio with a microphone, you are using the HFP profile to do that. That was working, so the audio part was working, but what we were missing was some controls to be able to send commands to the phone to, let's say, make a call or answer a call or put a call on hold. Now, with this functionality, PipeWire is now able to replace Ophono, which was the only project, like the only component that could do that before. And we decided to do that in PipeWire instead. It was somewhat simpler to add that in PipeWire. We also added the basic imaging profile support in BlueZ. The basic imaging profile is a profile that can transfer images through Bluetooth. We added like a subset of that is able to download the cover art from the media player, like for the media player that is on the car. If you're using something like Apple Music or Spotify on your phone, it's a requirement that you have the same information together with the album art on the infotainment system. That was merged in BlueZ, while the PipeWire telephony support is not yet merged. It lives in a merge request. It needs a little bit more attention from me. And we also fixed some other issues, mostly related to the audio-video remote control profile in BlueZ. Now, what were the challenges? As you can understand, we were working with people that came from a world where they only knew about how the proprietary stacks work. And for me at least, I didn't know how the proprietary stacks worked. So I lived in my BlueZ open source world, and they lived in their proprietary world, and we had to understand each other. So as we moved along the project, we found these differences. We found what is different. On proprietary stacks, it is very common that the Bluetooth controller is exposed as a serial device, and then you have a user space daemon that, which is the proprietary stack. This is the software. This is the proprietary software that basically grabs the serial port and then talks with the controller using the HCI protocol. That's the host controller interface protocol. There's nothing in the kernel space except for the serial driver or something like that. And it is probably good architecturally for the people that implement this daemon, because they can reuse the same thing in other operating systems. So this doesn't matter if you're implementing this on Linux or something else. It's just a serial port as far as the operating system is concerned. Now with BlueZ, this is different. The serial port is attached directly inside the kernel. The kernel then the kernel actually implements internally the main Bluetooth protocols. Like it talks HCI with the controller. It exposes L2 cap, which is a higher level protocol, and SCO, which is another higher level protocol. And you can basically request sockets from the kernel, and these sockets have the Bluetooth address family, similar to how we have the internet address family, and we have TCP, IP, UDP sockets, right? So that makes sense. Yeah, that makes sense, but it is different, like from what people are expecting. Now, some other expectations that were different, and things that we were looking at. One is that in BlueZ, if you're using BlueZ, the profiles are not really implemented in one place. You don't have one daemon. You have multiple daemons and multiple components in those daemons, multiple versions, because they are different projects. And you cannot really say that this version of BlueZ supports Bluetooth 5.2, for example, or 5.4, or 6. There's no such thing. You have to collect the pieces based on the version of the Linux kernel that you have, based on the version of BlueZ that you have, the version of PipeWire, bring it all together, bring in whatever UI that you have or other management software that you may have to make this all work. And then you have to assess what version you are supporting. Like you have to run actually the tests. You have to do the testing and say, okay, this supports this feature, take the list from the Bluetooth qualification, look at each test and say, okay, this checks out, so this is what we support. But yeah, that wasn't something that people were expecting, so they were asking like, okay, which version of Bluetooth does this version of BlueZ support? And we're saying there's no such thing. Another thing is there's no straightforward way to filter the HCI packets, which sometimes can be a security requirement to implement firewalls, like to filter what is going on between the controller and the host. Unfortunately, there is no, even though the architecture looks similar to the internet address family, where we have netfilter in the kernel, where we can filter the packets, there is no such thing for Bluetooth. There are some solutions, but they're not as straightforward as it is with internet packets. There's no support for containers as well, so right now it is a requirement that you run BlueZ on the host operating system, on the host container. You cannot really isolate using network namespaces and run the Bluetooth D in a different network namespace than the main one. These are fixable, of course, but need some work. Other differences that we saw is BlueZ hides complexity in general. It tries to be abstract. It tries to provide you with a nicer interface. But the customer code base had been already developed using the proprietary stack, so they had access to low-level information before. And that was clashing sometimes. Like the logic that they were implementing didn't match exactly to the logic that BlueZ exposed. So we had to work around that. They were also using a lot of logging to monitor things, like to monitor problems. We had to add some logs also in BlueZ and PipeWire all around the place just to make sure that they collect all the information. Also, they were expecting to collect the logs from one place, from one daemon, and that was no longer the case. Depending on which profile you wanted to debug, you had to look at different daemons and different logs and correlate information, and that is more challenging. Sometimes there's not enough error granularity in BlueZ as well. So one use case that I can remember is you have a phone that disconnects, and BlueZ says it disconnected. But why? There can be a number of reasons why it disconnected. It could be because the user just disconnected it manually. It could also be because the phone went out of range. And these are different use cases, but there is no such information given in BlueZ. While there was in the other stack. And also, BlueZ maintains state. So Bluetooth T, for example, maintains the list of paired devices internally, and it has that in a directory structure. That wasn't the case with the proprietary stack. And there was another layer that was already doing that in the customer's middleware. And when we discovered that, we realized there was some friction there because the higher level middleware was already trying to do stuff that we were already doing and sometimes mismatching with BlueZ. Another pain point is vendor-specific HCI commands. So HCI, as I said earlier, is the host controller interface. It's the protocol that you talk to between the host SoC and the controller. There are standardized HCI commands to talk to controllers, but there are some vendor-specific as well. Like vendors add stuff to make sure that they implement custom functionality. It affects many profiles. We actually found many profiles that needed vendor-specific HCI commands, and that wasn't easy to handle. One particular that I personally handled was the HFP profile, the hands-free profile, which typically on embedded systems, the audio that goes from the phone to the Bluetooth chip, it doesn't pass to the main SoC, but instead there is a hardware path between the controller and the audio DSP where the audio travels directly through the hardware path, and the main SoC never gets the audio. And that's a little bit obscure. We don't exactly know how that works. Every vendor has a different way of implementing that. And in the case of the particular chip that this customer is using, in order to make this hardware path work, we had to send vendor-specific commands to configure the audio format, the sample rate, like the codec that was being used, and things like that. And we had to do that every time that the audio path was opened and then closed. So every time that you had a phone call, you had to send these commands to open the path, and then as soon as the phone call stops, send the commands again to close the path and continue, which is pure unnecessary pain. This should have been part of the driver. Like this is something that belongs in the kernel, really, and it's so static. Like the format, the sample rate, etc., are static information that depend on how the chips have been wired together. It doesn't depend on parameters that come from the phone or anything. So it's really information that could be encoded in the device tree or somewhere else to make this work, but it's not there. And yeah, that's a pain point. We had to patch user space to do that. User space sending HCI commands to enable that path. And with that comes the next problem, which is security concerns of doing that. So if you allow user space to send HCI commands, you need to give it capabilities. And the first capability you need to do is to give the network row capability that allows sending row packets. With some commands, some functionality, we also needed CAPNet admin, so we needed to be root. On this particular system, nothing runs as root. They are all isolated. They are given capabilities one by one, and the customer was not pleased, obviously, when we decided to add CAPNet row to PipeWire in order to be able to send these commands to enable the audio path. I'm happy they were not pleased. That's actually a good thing. They care about security. That's good. And well, eventually we found a solution to that, which was very specific to their system, and it's not something generic. We need to, for a generic solution, we need to really fix that somewhere else. I think the kernel is the better place. Also, there were questions about the BlueZ daemon itself requiring those capabilities. Like they asked, why does BlueZ require CAPNet admin to run? But the answer there is that this is part of the BlueZ design. So BlueZ requires these permissions so that it can execute privileged operations, which is a security feature. Basically, the kernel only allows the Bluetooth D daemon to run those operations, and everybody else has to talk to Bluetooth D through dbus, instead of having all the user space components talk directly to the kernel and try to do privileged operations. That would have been a disaster. And some non-challenges, something that we thought was a challenge, but it wasn't eventually, vCard parsing. So vCard is the file that describes contacts. When you download contact lists from the phone, the contacts come as vCard files. And initially we thought, okay, we need to find a parser for this. We looked at parsers. We found parsers in GNOME, in KDE, other places on GitHub. They were too hard to package, too many dependencies. And then we looked at automotive-grade Linux, which had something else. It had actually a parser itself, like it was a very simple parser there. And we adopted that solution. We implemented vcard parsing again, which is so simple, it's much easier to write a parser than to package any library. Now, next steps. This project concluded, of course, for the community. The things that have been contributed are there. All the open source bits have been upstreamed or have been pushed to merge requests. Something that I would like to do after that is to expose the telephony bits of PipeWire to the desktop. So have like an application that you can make calls. I've seen GNOME calls exist, which is possibly an interesting target. Maybe there are other desktop apps that I haven't looked at yet. But yeah, I was thinking that the functionality that you have on the Mac, for example, where if you receive a phone call, it automatically shows you on the laptop that you have a call and you can answer from the laptop directly. That's something useful. And hoping to get that also into automotive-grade Linux, like to get all the changes into automotive-grade Linux again and have a demonstrator again in 2025. Thank you very much. Questions?
Do we have any questions?
So you touched mostly upon all the challenges for implementing this. Were there also some notable advantages over choosing this open source stack over the proprietary solution?
No. The goal was to achieve feature parity. The advantage is open source, right? So the customer wanted to use open source for the future to have access to the source code and be part of the community. That was the reason. No technical advantage.
So I know most of the proprietary Bluetooth stack solutions, the vendors basically say, well, we've tested with this, several hundred phones. Is that something your OEM customer worries about, or is there a discussion about trying to enable more testing against BlueZ upstream?
So in our case, no, we didn't care about these hundreds or thousands of phones. We mostly cared about 5 or 6 specific ones that are, the 99% of phones that are being used by their customers, because they have the telemetry data to understand which phones are being used the most. So that's what we test with. Yes.
How did you solve the who owns the data about paired devices? Did you be your customer, or did you change BlueZ?
We modified the customer's logic there. So we kept BlueZ as it is. So BlueZ maintains the paired devices, and the layer above adapts.
Yep, I think that's the end of the time.
Right, thank you very much.